everyone. So today we are going to be graphing. We're going to do three different types of graphs today: absolute value graphs, radical graphs, and piecewise graphs. So this might be a little bit longer of a lesson. But first, let's look at the do now. It says if f of 1 is equal to 7 and f of n is equal to 6 fn minus 1 minus 1, then what is f of 3? Now, something very important is here, and it's this f of n minus 1. If you recall, this f of n minus 1 represents the previous term. So when you have the previous term, we're talking about a recursive sequence. So in a recursive sequence, in order to find the term that you want, you have to find all the ones before that. So this is f3. That means we need to find f2 and we need f1. So first, f1, this here represents our first term. It is 7. So there we go, f1 is 7. Now to find all of the other terms, we have to use the rule. So I'm going to clear this up a bit. So we're using this rule here. So f of n, we're plugging in 2 for n, is equal to 6 times remember, f of n minus 1, that whole thing represents the previous term. The previous term is the term before, and the term before here is 7. So 7 is going to go in that parenthesis. So 6 times 7 minus 1. Now you can use your calculators. So you would do 6 parentheses 7 minus 1, and you get 41. So we don't have our answer yet. That's f of 2. So now we look for f of 3. To find f of 3, we use the same exact rule, but now n is 3. So we have 6 times the previous term. Now the previous term is no longer 7. The term before f of 3 is f of 2. So 42 is now going to go in that parentheses. We can't forget that minus 1 at the end. We can go to our calculator. 6 times 42 minus 1 gives us 251. So that tells us that f of 3 equals 251. Okay, so moving on to graphing. The first type of graphing we are going to do is absolute value. Now, for this lesson, you are definitely going to need a calculator. So make sure you either downloaded the calculator apps on your phone, you're using the Delta Math calculator, or you have a calculator of your own. So absolute value functions. It measures how far a number is from 0. So the absolute value symbol are those two straight lines. So here the absolute value of 5. 5 is 5 spaces away from 0. So the absolute value of 5 would be 5. Negative 6 is 6 spaces away from 0. So the absolute value of that is 6. Notice the absolute value will always be a positive number. It is never going to be a negative number. Okay, so all absolute value graphs have a V shape. We are going to see what that means in a bit, but we do need to go on to how to find absolute value functions on the calculator. So to find it, there are a couple of different ways. This is the way I like the most. Press second. Press 0, which is catalog. The first one that comes up, ABS, that is your absolute value. So let's say going back here, we wanted to find the absolute value of negative 6. So if we were to type negative 6 in there, it would give us 6. So let's get to graphing. So y equals the absolute value of x. This is called our parent function. That means that nothing is done to this absolute value of x. So we're going to graph it. To graph it, we're going to use our calculator. We're going to go to y equals, and we're going to type in the absolute value of x. So second, 0, absolute value, and x. So first things first, this is what the graph looks like. But to get exact points, we go on the table. Now, looking at this table, you want to get some positive values and some negative values. Kind of similar to graphing quadratics, there is a pattern when it comes to absolute values. Notice here, everything on this side is the same exact thing on this side. So it's very similar to graphing quadratic functions. Now I'm going to slide the table onto here. So I have it. And then we're just going to plot these points. Okay? So our first point here that I want to plot is 0, 0. Now that is the vertex, okay? It's where that pattern is it's a point that's in the middle of that pattern. Now we have 1 and 1. So right over here, we have 2 and 2, 3 and 3, 4 and 4, and so forth. And we have that same pattern in the negative side. Negative 1, 1, negative 2, 2, negative 3, 3, negative 4, 4, and so on. And then that was a horrible line. And then that's a little better, still bad, but that's as good as I'm getting here, guys. You connect the lines. Okay? You see what I mean. Sorry, my lines are not that straight. But that is the parent absolute value function. Now let's get to graphing something that's not the parent function. So here, let's graph the absolute value of x minus 2. So we're going to go back to our y equals. To get the absolute value, second, 0, enter. So the absolute value of x minus 2. Then we go to the table, second graph, to get our table. Always good to look for that middle point, so you want to look for that pattern. So that pattern is right over here, and I'm going to drag it onto this page. So let's graph it, starting with the vertex. So the middle of the pattern was 0, negative 2. So we have 0, negative 1, negative 2. Then we have 1, negative 1. Then we have 2, 0. Then we have 3, 1, and so on. If you want to graph your points all the way up, by all means. Going in the opposite direction, we have negative 1, 1. Then we have negative 2, 0. Then we have negative 3, 1, and so on. Again, you can go all the way up if you'd like. So now here, it continues. Okay, that was a little bit better. All right, so part B says state the range. If you recall, the range are your y values, okay? So it goes from lowest to highest. So remember, it was some number less than or equal to y, less than or equal to some number. Now this was usually your lowest point, and this is usually your highest point. So this is one way to write the range in interval notation. So if we look at our graph here, our lowest point is at the vertex. That's our minimum value. And on the y-axis, that is at -1, -2. So -2 is our lowest point. Looking at our highest point though, we have arrows. If we were to look at our table and keep going up and up and up, those values are not going to stop. They're going to keep increasing. So that tells us that our graph goes towards infinity. Now, if you recall, whenever you are finding the range, if you have infinity, you can't ever equal infinity. So you just want to get rid of that or equal to line underneath. So that would be the range of this graph. Part C says explain how g of x, which is the absolute value of x, was changed to obtain f of x, which was the problem that we just had, the absolute value of x minus 2. So what I'm going to do is I'm going to go to the calculator, I'm going to go to y equals, and I'm going to type in both of them. So here was our f of x, but in y2, I'm going to type in regular the absolute value of x. So the red line is our original line. The blue line is our new one. To get from red to the blue, we have to go down 2 spaces. So that's how g of x was changed. So you shift down 2 spaces. Notice I mentioned direction and I mentioned the number of spaces that I moved. Okay, so moving on to the last problem with absolute value. It says graph the equation f of x equals 3 times the absolute value of x minus 4. So going to the calculator, clearing everything out, and typing it in. So 3 absolute value of x minus 4. So now I'm going to go to my table. I don't see a pattern here yet, so that means I'm going to have to look through. So I'm going to scroll up, and I found the pattern. Here's the middle of it at x equals 4. So I'm going to drag that here so I can graph. So I'm always going to graph the vertex first. The middle of the pattern was 4, 0. Whoops. The middle of the pattern was 4, 0. So we go 1, 2, 3, 4, 0. Right there. Okay. Then we have 5, 3. So 5, 1, 2, 3. Then we have 6, 6. So here's 6, 1, 2, 3, 4, 5, 6. And so on. Now I'm going to do the other side of the vertex, which is at 3, 3. So 1, 2, 3, 1, 2, 3. Then we have 2, 6. So 2, 1, 2, 3, 4, 5, 6. And so on. So now I'm going to connect it. Notice I forgot, oh my goodness, I'm going to get a straight line here. Notice when I was connecting these, I was using a point at the bottom, so it makes a V shape. That's how you should be connecting your graph. It should make a sharp turn and it should form a V. Okay, now that we have the graph made, let's state the range. So remember, it's some number less than or equal to y, less than or equal to some number. This number being the lowest point, this number being the highest point. So here's our y-axis. The lowest number that our graph gets is going to be on the vertex. The vertex, the y value of that point is 0. So this is 0. The highest point of this graph, notice we have arrows, that means it's going to keep going up and up and up and up, is infinity. So what we have to do is just get rid of this or equal to sign, and there's our range. Now another way to write this is with the parentheses or the brackets. Remember, brackets means the point is included. So 0 would be included, and you use parentheses when the point is not included, such as infinity, because you can never equal infinity. Okay, so that was part B. Moving on to part C, it says explain how g of x equals absolute value of x was changed to obtain our graph here. So I'm going to do the same thing as last time. So we already have our graph in. Now for 2, I'm going to put in the absolute value of x. Now let's see how it changed. So we're looking from the red to the blue. Now, if we look, it obviously shifted to the right. It shifted to the right 1, 2, 3, 4 spaces. But if we see, it also got narrower. The red one opens up a lot wider than the blue one. So we're going to say it shifted 4 units right and became more narrow. Okay, so moving on, we're going to go to radical functions. So radical functions, they take the square roots of a number. So a radical symbol is this symbol here. We've seen it before. Some examples of radical: the square root of 9 is 3. The square root of 25 is 5. Okay, you can find this in your calculator. To get it in your calculator, you press second and then x squared. So if we wanted to find the square root of 25, we would do it that way. Okay, so these are the steps on how to get the radical function in the calculator, which is what I showed before. Now, all radical graphs have the same shape. They look like this. We are going to see it in a bit, but they look like this. It's kind of an odd shape for a graph, but it starts at a specific point and then it curves over. So let's see what that looks like. So y equals the square root of x is called our parent radical function. So let's graph it. We graph it the same way with our calculator. So I'm going to clear everything out. Then I'm going to type second square root of x. Press the graph to show the shape that it's going to look like. Now let's get the actual points here. But now, there's a lot of weird stuff going on here. We have some errors, we have some decimals. What you only want to look at is where the first error starts. So, we don't care about any of these points. Our first point is going to be 0, 0. Now, notice all of these other points, all these decimals. We can't graph those. So, we don't. We only graph the whole number points. So I'm going to move this here. If we look, this is the first error. That means we're not going to have any graphs where that error is. Our graph is going to start at 0, 0. So that is our first point. The next point is 1, 1, which is right over here. We can't graph 2 and 1.4142. Okay, we don't graph decimals, so we just don't do it. Not graphing that point. We're also not graphing the 3. The next point we can graph, though, is 4, 2. So 1, 2, 3, 4, 1, 2. Can't graph 5, can't graph 6, 7, or 8, but we can graph 9. So it'd be 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 3. 1, 2, 3. Those are the only points we can graph on this graph. So we connect them and put an arrow at the end. This is our parent function for the radical equations. So we're going to go through a couple of examples. First, graph the equation f of x equals the square root of x minus 1. So going here, typing in the square root of x minus 1. Notice that this minus 1 is underneath the radical. When you type it in your calculator, it has to stay under the radical. So this is what the graph is going to look like, but we need exact numbers. So we press second graph. You want to look for the errors because you know right beneath that is where the first point of your graph is going to be. So I'm just going to drag this down here. And let's get these values graphed. So we can't graph any of our errors. Okay? The first point we can graph is 1, 0, which is right here. We can graph 2, 1. We can't graph 3, can't graph 4. We can graph 5, 2. 1, 2, 3, 4, 5, 1, 2. And that's enough points for us. We can connect and put our arrow. Notice I don't have any graphs below our first point. That's because every point below it has an error. That means we can't graph it because it can't happen. The reason being is if you were to have that number under the radical, you get a negative, and you can't have a negative radical. So that's why we only put the arrow on one side, not the other. So now let's write the domain and the range. So the domain are your x values, the range are your y values. We're going to write it in interval notation. So some number less than or equal to x less than or equal to some number. This first number here is our leftmost point. And the number that goes here is our rightmost point. So if we look at our graph, the point all the way to the left is this one here, and that x value is a 1. So our leftmost point is 1. As for our rightmost point, we have this arrow going on, which means it's going to go on for forever and ever and ever. And when that happens, we have an infinity. So since we have infinity, we can never equal it. So I'm just going to get rid of that right there. Now moving on to the range. So we have the lowest number, less than or equal to y, less than or equal to the highest number. So again, this point right over here, that's our lowest point. There's nothing below it. The y value there is 0. The highest value, I know it kind of seems like this should be it because it's our only point there, but all of these points are above there, even if we don't have the exact point. So it's going to keep growing and growing and growing, even if it's a slow growth. So I'm going to look at our table here. You notice the points keep going up and up. It's slow, but it's still going. So that tells us that our highest point is infinity. Since it's infinity, you can get rid of the or equal to. Now, since we already did a couple of range questions, here was something else that we did talk about. If you have an infinity, you can kind of get rid of this from interval notation and leave it as that. Okay, so keep that in mind as well. That's just another notation for finding the range. You can also do the same with the domain since you have an infinity here. So last question, explain how g of x equals the square root of x was changed to obtain f of x, which is our graph. So we're going to type them both into y equals to compare. We already have what ours is. Let's write the original, and this is what we have. So to get from the red to the blue, it looks like we had to go over 1 point to the right. So to get from here to here, we shifted 1 to the right. So that's what we're going to write here. Shift 1 unit right. Okay, so moving forward, we're going to do one more example, and it says graph this equation. So go to our calculators. We're going to be using our calculators for everything today. Okay, we go to y equals second square root of x. Notice this plus 3 is not underneath this radical. It's on the outside. So make sure you type it in as such. Press the arrow. Plus 3. Let's look at our table. Remember, you want to look for the errors. So I'm going to scroll. Found it. So now this is where my graph is going to start. So I'm going to take this and graph the points that are on here. So I can't graph the errors, so I'm just going to cross those out there. First point I can graph is 0, 3. So 0, 1, 2, 3. Next point I can graph is 1, 4. Can't graph this, can't graph that. I can graph 4, 5. So 1, 2, 3, 4. 1, 2, 3, 4, 5. And I can't graph any of the rest of these. Okay, so 3 points should be enough. Remember, it starts at that first point. You can't go below it. And you draw your arrow just on the one side, not on the other side. So let's find the domain and the range. So the domain are your x values, remember. So some number less than or equal to x, less than or equal to some number. The leftmost point is this point right here. It's the one all the way to the left. And the x value at that point is 0. So our domain starts at 0. And it's going to keep going and 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 going. That's what the arrow represents. So it goes on to infinity. Since it does go on to infinity, you can kind of forget about all of this and just leave this right here as your answer. So this is just saying that x is greater than or equal to 0, or 0 is less than or equal to x. Moving on to the range, those are your y values. So you want to look at the lowest point to the highest point. So some number less than or equal to y, less than or equal to some number. Our lowest point is this point as well, and it is at 1, 2, 3. So our lowest point is 3. Our highest point is going to keep growing and growing and growing. So it is infinity. Since it is infinity, you can get rid of this whole inequality here and just be left with this for your range. So again, I'm just doing this to show different representations of the range. If you wanted to include the infinity in your answer, by all means, that is fine. So now we're going to explain how it changed. So going to the graph, here is what our question had. We want to see how it changed from the square root of x. So now let's look. So the red is our original, the blue is our new graph. It looked like it went up, and it went up by 1, 2, 3 units. So shifted up 3 units. And that is radical graphing. So going on to the last type of graphing we are going to do, it is going to be piecewise functions. So piecewise functions is a function that has multiple parts, okay? So this is what a piecewise function looks like. It has g of x, which is a function, and it splits it up. So this is saying that, I'm going to split it up by a line, that when x is less than 2, use this equation. And this is saying when x is greater than or equal to 2, use this equation. So it looks something like this. It looks like two separate graphs, but they are put together because they're domains. So when you have an open circle, that means the point is not included in the graph. When you have a closed circle, that means the point is included on the graph. For example, here we had a closed circle. That means the point was included. Here we have an open circle. That means the point was not included. So let's actually get to graphing these. So to graph, we're going to make a table for each function. So we're first going to graph it. Don't worry about A, B, and C. We're going to make a table for both of these functions separately first. So here we're given two equations. I'm going to split it across the middle to show the two different ones. So here's the first, 3x minus 2. Now that happens when x is less than 3. So we're going to write 3x minus 2. We're going to get some values for x. Now, we need values where x is less than 3. Okay, 2 is less than 3. 1 is less than 3. 0 is less than 3. Negative 1 is less than 3. All of these values are less than 3. Notice I didn't include 3 because it didn't say less than or equal to. Now what we're going to do is we're going to go to our calculator to get these values. So we're going to go here and we're going to type in the function. It was 3x minus 2. So I'm only focusing on that one graph for now. Second table. Now I'm going to look at the x values that I wrote down. If you wanted to write down different x values, that's fine. If you want to go to -2, -3, that's fine. As long as it doesn't start at 3. It's strictly less than 3. Okay? So when x is 2, we have y to be 4. So that's going to be our first one. Now when x is 1, y is 1. When x is 0, y is -2. And when x is -1, y is -5. So this is our first graph. So I'm going to graph this one. So we have 2, 1, 2, and 4. 1, 2, 3, 4. We have 1 and 1. We have 0 and -2. And we have -1 and -5. Notice you could have also graphed this using the slope and y-intercept, but you have to be careful. Now this is where the tricky step comes in. I know that x has to be strictly less than 3, but you still need to include the point on that graph. So here, when x is 3, y is 7. But look at what I'm going to do. So here we have 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. I am going to draw an open circle because x is not equal to 3. But we have to keep in mind that there are values between 2 and 3. So we're only going to draw the arrow on the side of the line that is where our values lie. So that open circle is for when x is 3. So that is our first graph. Now we are going to focus on this second one, which is -2x plus 7. Now, the domain of this graph is when x is greater than or equal to 3. So that means we can start at 3. And then we get values that are greater than 3, like 4 and 5 and 6 and so on. So now we're going to get rid of this graph, and then we are going to type in our new one. -2x plus 7. Okay, now we're going to look at our table. So we want to start at 3, because that's the first possible value. And the y value here is 1. So we have 3 and 1. Then we have 4 and -1. We have 5 and -3. And we have 6 and -5. Okay, So we're going to graph this separate from the one that we did in blue. So we have 1, 2, 3, and 1. Now this is a closed circle because this is or equal to. Then we have 4 and negative 1. We have 5 and negative 3. We have 6 and negative 5. And you can go further if you'd like, but we are only graphing, connecting the points beneath it. We are not drawing the arrow the other way. Notice the two lines do not intersect, and they shouldn't. Now this is how we graph piecewise functions. Just looking at A, B, and C, you can use your graph to answer these. Your tables. So f g of 6. Now 6 is not in this first graph because this graph is less than 3. 6 is not less than 3. So we had to use the second equation. Now we did use this value in our graph. G of 6 is a negative 5. Now looking at negative 1. Negative 1 is less than 3. So you would use the first equation to find it. We use that in our graph and we get negative 5 as well. Now G of 3. 3 is not included in this first graph. It is included in the second one. So when x was 3, y was 1. So that is one example of a piecewise function. Moving on to our last example of a piecewise function. So here, again, I like splitting it in half so I can treat it as two different graphs. So I'm first going to graph what is on top. Now we have x squared minus 5. Now this is true when negative 1 is less than or equal to x, which is less than 3. What this is saying is that x is in between negative 1 and 3. However, 3 does not have an or equal to sign underneath. So it is not including 3. Okay? So if we were to make our table of values, the first point that we're going to use is negative 1. Then comes 0. Then comes 1. Then comes 2. But we cannot include 3 in what we graph. So let's go graph this first one. It is x squared minus 5. Whoops. So x squared minus 5. I'm going to go to the table of values. So remember, we only care about these specific x values. So starting at negative 1, when x is negative 1, y is negative 4. When x is 0, y is negative 5. When x is 1, y is negative 4. When x is 2, y is negative 1. Now we can't forget that we need to have 3 on our graph, but put an open circle. But I'm going to hold off on that for a second. Let's graph what we have. So we have negative 1, negative 4. Then we have 0, negative 5. Then we have 1, negative 4. We have 2, negative 1. Now we're not including 3, but we still need to make it an open circle at 3, 4. So we have 1, 2, 3, 1, 2, 3, 4. Open circle. I don't include it in my chart because it needs to be an open circle. Now I connect it. I'm not putting any arrows on my graph because x is only between these 2 points. It can't be any other value. So now the blue graph is done. Let's look at the second one, which is 2x minus 1. Now let's look at what this means. This means that x is in between 3 and 6. Since both of them are or equal to symbols, both of those numbers are included. So we have 3, then we have 4, then we have 5, then we have 6. So let's look at it in our table. So 2x minus 1. Press second table. First one we care about is 3. So when x is 3, y was 5. When x is 4, y is 7. When x is 5, y is 9. And when x is 6, y is 11. So let's graph this. So 1, 2, 3. 1, 2, 3, 4, 5. Then we have 4, 7. Then we have 5, 9. And we can't fit anything else on this graph. Now the arrow is only going to go one way. It's only going to go above. Okay, sorry, that was not a very good line. Let me maybe redo that. It's only going to go above because the graph cannot be beneath 3. Okay, so there is our piecewise graph. Now let's answer these questions. So first we want to find P of 3. That means we're going to be looking at the second equation because 3 is included. And we found y to be 5. Looking at 0, 0 was included in the first equation, which was negative 5. Then we're looking for 5. 5 was in the second equation. That's where x is 5. And that was equal to 9. Okay, so that's all the questions. Make sure you do the group practice in order to get credit for this video.